Good day, everyone. Welcome to Transmission Media and Antenna Systems. I am Jessica N. Belien from EK31 under the College of Engineering and Technology at Universidad de Manila. In this lesson, I'm going to discuss the fractal antenna guided by our Professor Engineer Brian Dineros. Fractal Era. Dr. Cohen built the first bona fide fractal element antenna in 1988. He is now one of the world's most innovative antenna designers. Now, with 26 years of professional experience and 53 years of practical experience, stemming from his ham antenna work over many years. Cohen has been a leading force in the commercial adoption of fractal antennas. The picture is the first manufactured fractal antenna sheet circa 1995. Upon their discovery, Cohen and other pioneers in the field faced tremendous inertial resistance to this new breakthrough technology by incumbent vested interest. However, over the last 2 decades, the technology's benefits have become well accepted, having been proven time and time again. Fractal antennas are now ubiquitously applied in commercial and government applications around the globe. The founding of Fractal Antenna System Inc. In 1995, Cohen co-founded Fractal Antenna Systems Inc., now in Bedford, MA, and has held position as CTO chairman and his present position of Chief Executive Officer. Over Fractal's 24-year history, Dr. Cohen has been a central force in the commercial success of the company. In the early days of the company, he was instrumental in laying the technical foundation and educating the market of the benefits of fractal antennas. With this baseline, he has successfully guided the company through the rapidly changing currents of the wireless industry. Over this history, Fractal has developed a presence in nearly every antenna end market, from devices to infrastructure to government. Today, the company continues to push the boundaries of wireless communications, applying our technology to emergent fields such as 5G, commercial millimeter, and IoT. Fractal term was first coined by Benoit Mandelbrot in 1983 to classify the structure whose dimensions were not whole numbers. One of the properties of fractal's geometry is that it can have an infinite length while fitting in a finite volume. The radiation characteristic of any electromagnetic radiator depends on electrical strength of the structure. Using the property of fractal geometry, we may increase the electrical length of an antenna, keeping the volume of antenna same. There are an infinite number of possible geometries that are available to try as a design of fractal antenna. Let's try to answer some questions. So now, let's discuss what is fractal antenna. Fractal antenna is an antenna that employs or utilizes a fractal design which is approximately or exactly similar to a component of itself, with an aim to increase the efficacious boundary length or perimeter of the material that can accept as well as channelize electromagnetic radiation within a provided area or volume. Fractal antennas are an integral part of electronics and radio communication. Research into more practical uses of fractal antennas is being carried out and in future. We can see them used in plethora or real-world application around us. In mathematics, fractals are an abstract object which is used to display patterns expanding at a small scale. They are also known as expanding or evolving symmetry. Since fractals show up in the real world of nature, such as snail shells, leaves on a tree, pine cones, why not see if they perform well as antennas? It turns out that if you make antennas with fractal shapes, they will radiate and often have multi-band properties. Application. The first application of fractals to antenna design was thinned fractal linear and planar arrays, arranging the elements in a fractal pattern to reduce the number of elements in the array and obtain wide bands array or multiband performance. Another advantage of these fractal arrays is that the self-similarity in their geometric structure may be exploited in order to develop algorithms for rapid computation of their radiation patterns. These algorithms are based on convenient product representations for the array factors and are much quicker to calculate than the discrete Fourier transform approach. Cohen was the first to develop an antenna element using the concept of fractals. He demonstrated that the concept of fractal could be used to significantly reduce the antenna size without generalizing the performance. Puente et al. Demonstrated the multi-band capability of fractals by studying the behavior of the Sierpinski monopole and dipole. The Sierpinski monopole displayed a similar behavior at several bands for both the input return loss and radiation pattern. Other fractals have also been explored to obtain multi-band or ultra-wideband antennas. Fractal antenna elements. The fractal concept can be used to reduce antenna size, such as Koch dipole, Koch monopole, Koch loop, and Minkowski loop, or it can be used to achieve multiple bandwidth and increase bandwidth of each single band due to the self-similarity in the geometry, such as the Sierpinski dipole, Cantor slot patch, and fractal tree dipole. In other designs, fractal structures are used to achieve a single very wideband response, the printed circuit fractal loop antenna. These are the picture of various fractal antennas element. Letter A is Koch dipole, letter B is Koch loop, letter C is Sierpinski dipole, letter D is Cantor slot patch. First, Koch monopole and dipole. The Koch curve has been used to construct a monopole and a dipole in order to reduce antenna size. In Figure A, the first resonance of a Koch dipole is at 961 MHz, while that of a regular dipole with the same length is at 1851 MHz. Therefore, the length of the antenna is reduced by a fact of the 1.9. The current distribution and the radiation patterns for both the Koch dipole and the regular dipole at the resonant frequencies are shown in Figure B. It is worth mentioning that the radiation pattern of a Koch dipole is slightly different from that of a regular dipole because its fractal dimension is greater than 1. Koch loop and Minkowski loop. The Koch curve has also been used to form a loop or reduce size. Another example is the Minkowski loop formed with a 90-degree bend. Both types of fractal loops can reduce the diameter of the loop and achieve approximately the same performance as a regular single while loop. Third, Sierpinski monopole and dipole. The Sierpinski gasket is a self-similar structure. In an ideal Sierpinski gasket, each of its three main parts is exactly a scaled version of the object, scaled by a factor of 2. The self-similarity properties of the fractal shape are translated into its electromagnetic behavior and results in a multiband antenna. The variation in the antenna's flare angle shifts the operating bands, changes the impedance level, and alters the radiation patterns. Fourth, Cantor slot patch. The Cantor slot patch is another example of multiband fractal structure. This type of patch has been applied in multiband microstrip antennas and multiband frequency selective surfaces. 5. Fractal tree. Various fractal tree structures has been explored as antenna elements and has been found that the fractal tree usually can achieve multiple wideband performance and reduce antenna size. 6. Printed circuit fractal loops. The printed circuit fractal loop antenna is designed to achieve ultra-wideband or multiple wideband performance and significantly reduce the antenna dimensions. The antenna has a constant phase center, can be manufactured using printed circuit techniques, and is readily conformable to an airframe or other structures. The picture is the coach dipole and regular dipole. Letter A is input impedance of a coach dipole. Letter B is current distribution of the coach dipole at 961 MHz. Letter C, current distribution of the regular dipole at 1.851 GHz. Letter D, 3D radiation pattern of the coach dipole at 961 MHz. Letter E is 3D radiation pattern of the regular dipole at 1.851 GHz. How it works. Basically, antennas produce energy when electrons are moved from one end of an antenna to the other, and fractals are the shapes that constantly repeat themselves. In a fractal antenna, both these concepts are merged together and they work beautifully in cohesion. In an antenna, it is pretty essential to move the electrons at an optimal rate to ensure great performance by the antenna. This rate relies on the length of the antenna. In case of fractal antennas, the shapes constantly repeat themselves but exist at varying lengths. This allows a fractal antenna to work for multiple rates rather than a single rate in case of a normal antenna. Hence, multiple frequency can be used in the case of a fractal antenna. This property of fractal antenna holds a high level of importance in various applications that work on varying frequencies. In general, the fractal parts produce fractal loading and makes the antenna smaller for a given frequency of use. Practical shrinkage of 2 to 4 times is realizable for a given performance level. Multiband behavior is manifest at non-harmonic frequencies, while some bands are broadened. At the given frequencies, the FEA is extremely and naturally broad band and can be made frequency independent without a log periodic geometry. Shrunken, very wide band FEA are possible. Arrays naturally benefit as well, as the arrangement of elements must be defined by Hogfeld-Cohen-Ramsey or HCR conditions for frequency invariance. Pacing and polarization control are also attainable in FEA. If they are so good, why are they not in use? This is a misconception. Our antennas are widely used in applications across many commercial and government applications. It is unlikely that you will see our antennas as they tend to be embedded inside products or under radomes. Like many breakthrough technologies, there was a fair amount of inertial resistance from incumbents in the antenna industry when our technology was first published. Such resistance to change has led to residual misconceptions about the limitations of fractals. These negative claims have been definitively disproved, as there are now 2 decades of academic studies and commercial experience to prove the superior performance of fractal antenna elements and arrays. Let's answer some questions. Benefits of using fractal antenna. First, only a single antenna can be used instead of installing many. This saves time, cost as well as leaves space for other components. Second, with the use of fractal antennas, the size of the end product reduces. Third, the combination of fractal technology and the concept of movement of electrons in antenna help to create small-size antennas which are more efficient as well as dependable as compared to normal big-sized antenna. Fourth, fractal antennas impart the property of being versatile to a single object, as with the inclusion of fractal antennas, many functions can be incorporated into a single object. Fifth, with the usage of fractal antennas, designs can be custom made according to the requirements, instead of having few fixed design in hand. This means, with fractal antennas, it has become possible to mold the design according to the requirements rather than molding the requirements according to the few fixed design options available. One of the most important benefits of fractal antenna is that we get more than one resonant band. The fractal concept can be used to reduce antenna size, such as Koch dipole, Koch monopole, Koch loop, and Minkowski loop, or it can be used to achieve multiple bandwidths and increase bandwidth of each single band due to the self-similarity in the geometry, such as the Sierpinski dipole, Cantor slot patch, and fractal tree dipole. Uses of fractal antenna. Since the fractal design of the antenna reduces its total size, it finds its usage in a variety of applications. First, RFID technology. The small size of fractal antennas makes them an ideal choice for radio frequency identification technology, or RFID. RFID is the utilization of radio waves to read and capture the data stored on an RFID tag which has been further attached to an object. Second, cell phones. The component which keeps your cell phones going is the printed circuit board utilized within it. The wireless capability has been provided to your cell phones by employing fractal antenna in PCB design. In fact, the wireless capability of a device increases and is enhanced by the use of fractal antennas. Third, high-definition televisions. You must be aware of earlier televisions which had only a single channel coming up a single frequency. You had to adjust the television's antenna to a particular angle to catch the right frequency. Now, there are multiple channels which work on different frequencies. This makes fractal antennas as essential component of your HD televisions. Since a television has to work at multiple frequencies, Fractal antennas prove a great help. 4. Counterpoise. A counterpoise is a term used in electronics and radio communication for a network of wires, cables, or a metal screen, which is utilized as an effective replacement for an earth connection in the system of the radio antenna. It is perfect when, due to certain conditions, a normal earth-ground system cannot be utilized. Fractal antennas are an effective and a vital component of the counterpoise. Beside the above, fractal antennas have found essential uses in fractal inductors, fractal resonators, tuned circuits, loads, and ground planes. In addition to their use as antennas, fractals have also found application in other antenna system components including loads, counterpoises, and ground planes. Fractal inductors and fractal tuned circuit, fractal resonators, were also discovered and invented simultaneously with fractal element antennas. An emerging example of such is in metamaterials. A recent invention demonstrates using closed-packed fractal resonators to make the first wideband metamaterial in visibility clock at microwave frequencies. Fractal filters, a type of tuned circuit, are another example where the superiority of the fractal approach for smaller size and better rejection has been proven. As fractals can be used as counterpoises, loads, ground planes, and filters, all parts that can be integrated with antennas. They are considered parts of some antenna systems and thus are discussed in the context of fractal antennas. Let's answer the final questions. Let's summarize the discussion. Dr. Cohen was built the first bona fide fractal element antenna in 1988. Fractal term was first coined by Benoit Mandelbrot in 1983 to classify the structure whose dimensions were not whole numbers. The first manufactured fractal antenna sheet circa 1995. Fractal antenna is an antenna that employs or utilizes a fractal design which is approximately or exactly similar to a component of itself, with an aim to increase the efficacious boundary length or perimeter of the material that can accept as well as channelize electromagnetic radiation within a provided area or volume. Various fractal antenna elements: Koch monopole and dipole, Koch loop and Minkowski loop, Sierpinski monopole and dipole, Cantor slot patch, fractal tree, and printed circuit fractal loops. Basically, antennas produce energy where electrons are moved from one end of an antenna to the other, and fractals are the shapes that constantly repeat themselves. In general, the fractal parts produce fractal loading and makes the antenna smaller for a given frequency of use. Fractal antenna mostly used in RFID technology, which is radio frequency identification technology, cell phones, high-definition television, and counterpoise. Only a single antenna can be used instead of installing many. This saves time, cost, as well as leaves space of other components. Fractal filters, a type of tuned circuit, are another example where the superiority of the fractal approach for smaller size and better rejection has been proven. With the use of fractal antennas, the size of the end product reduces. Thank you for listening and watching.